Hi, everybody. I am Armando Gallegos, and I'm going to talk about the positivity preserving finite difference scheme for a fractional non-local Fisher-Kolmogorov-Petrowski-Piskunov equation. I come from Universidad de Guadalajara, Mexico. Thank you for your attention. Okay, here we can see the contents of the presentation. Okay, here we can see the original problem is a non-local Fisher-Kolmogorov-Piskunov equation, where the difference with the original equation is this term, the non-local term, where the integral is included here in this term, and the function C is a kernel that satisfies this in this condition. Okay. Our idea is to extend this non-local problem to the fractional case using the usual Caputo fractional partial derivative that is defined in this part. So our main problem is described by this equation where the fractional part is included in this time derivative and the non-local part is defined by this term with this integral. And the equation is subject to these initial boundary conditions. So the aim of our work is to solve the integral differential problem with a finite difference scheme to show that the proposed technique is capable of preserving positivity and abundance of the solutions to prove the consistency and stability features of the scheme and to provide some computer simulations. Now let's review the numerical model. So let's review previously the nomenclature where M and N is natural numbers. Let's consider uniform partitions for the space and time. For A is in this set and N is in this set, and define these values in terms of the step size of the space and time. We propose the following approximations with the analytical solutions of our problem, and let's consider the following linear difference operator. Okay, in order to discretize the fractional Caputo derivative, we use the following definition by Schwann and Liu, where the Caputo fractional derivative is approximated by this expression, where the coefficients are defined by this expression. And the following lemma guarantees that the approximations are good until this order. So we propose the following finite difference scheme for our program, subject to these initial boundary conditions, and the main part of the equation, of course, is the fractional derivative, discretization, and the integral part discretization. So in this part, the Gn is obtained using the Gauss-Legendre quadrature. We can revise the letter and Davis article for that in order to approach the integral in our problem. Okay. More particularly, the Gauss-Legendre quadrature, the idea is to approximate this integral with this discretization, where eta k are the roots of the Legendre polynomial, and the weights are given by this formula, and this evaluation of the function can be can be written in these terms, and the x I is a point of partition that satisfies these conditions. If we use this identity for the discretization of the capital derivative, we can write our finite difference scheme in explicit terms. So this is our main proposal of finite difference scheme in explicit form. Now let's review the positivity and abundance of our scheme. So let K in this form and assume that the initial values are bounded and positive. And if tau satisfy this inequality, so the solutions are bounded and positive for our line. The proof is by induction, so we can note this identity and assume that the UN are bounded and positive. So it follows that this inequality is satisfied where kappa alpha is defined in this form and the last sum is null for 0 and 1. Here we use the fact that the integral parts are bounded for L sufficiently large according to Donaldson paper. In similar fashion as this paper, one readily checks that the right-hand side is increasing function of UN is if kappa alpha satisfies this inequality. Therefore, this inequality is valid, so we can guarantee the bounded of the solutions. On the other hand, the parameters beta, B, sorry, satisfy these conditions, then since all the constants are positive in our scheme, and by induction hypothesis, we have that U n plus 1 satisfy this inequality if kappa alpha satisfy this inequality. So we can conclude that if tau satisfy this inequality, we guarantee the positivity and boundedness for induction. Okay, here we can propose the existence of the solutions. And so if the hypothesis of the previous theorem are satisfied, then the solution of the proposed scheme exists. The proof, of course, is stronger because we guarantee the positivity and boundedness, and the method transforms into explicit technique. Now let's review the numerical properties. For the consistency, let's define the continuous and discrete operators, and we establish the following theorem about the consistency of our scheme. So the proof is using Taylor's theorem for the secondary spatial derivative. And for the integral part, we use the Abramowitz and Allen result. And we can guarantee this inequality. And for the fractional part, we can see that the parameters B can be written in this form, so this inequality holds. So using the triangles inequality and all the previous expressions, the proof is immediately. Okay, so about the a priori bonds, let UN be numerical solution of the find difference scheme, and suppose the conditions and positivity and boundedness so exist C, so that this inequality holds for all n. The proof is using again the same identity as the previous slide, and using again the these conditions for B, and it follows that for all n, this inequality is satisfied. Therefore, the following inequality is satisfied, and for all n, we have that this expression of is satisfied. And finally, rearranging terms and taking telescoping sum on the above bonds, we obtain the un minus u0 is equal to this absolute value, and the inequality holds. So, which implies the conclusion of the theorem. Okay, now with the stability of the order scheme, let UN and let UN tiled be numerical solutions of the finite difference schemes with the initial conditions U0 and U0 tiled, respectively. If the positive boundedness theorem hypothesis holds, then there exists a constancy independent of the initial conditions, so that this inequality holds for all. The proof is by induction. So consider the following function, where kappa is defined under previous, and h is written in terms of the discrete form of the integral. Now we take the partial derivatives, and the result is as follows. Now, by the main value theorem, there exists a omega in the segment of line between U and UN tile, so that this inequality is satisfied. Under the condition of the theorem and using the previous derivative, it's easy to see that this inequality is satisfied in similar fashion as our previous work. One verifies that this result is satisfied. So to complete the proof, we must define DC in these terms and apply induction. As a corollary of the previous theorem, we can prove the uniqueness of our scheme. So we'll let UN and UN tile be numerical solution of the finite difference scheme with the same initial conditions. If the positive unboundedness theorem holds, so of course U and U tile are equal. The proof is very easy. So by hypothesis, U0 and U0 tile are equal. We suppose that UN and UN tile are equal, and using the last result of the stability theorem proof, we can observe that this inequality holds. Of course, therefore, UN plus 1 is equal to UN plus 1 tile. So the result follows by induction. Finally, let's review some computer simulation. For the computer simulations, we use the following values: the initial function, this kernel, and these parameters. So we use a tau that satisfies the boundedness and positivity, and here is for alpha equal to 1, or for the integer case. This simulation is for fractional parameter 1.98 for 0.95 value of alpha, and for 0.90 value of alpha. So in this last example, we put a t value that doesn't satisfy the condition of positivity and boundedness, and clearly the scheme is wrong. Finally, the conclusions of our work: we have designed a finite difference scheme to approximate the solutions for a fractional non-local Fisher-Kolmogorov-Petrovsky-Piskunov equation. We employ an explicit finite difference scheme to solve the model. We establish rigorously that the scheme is capable of preserving the positivity and boundedness of the numerical solutions. We show that this scheme is consistent and stable, and we perform some computer simulation of the numerical model. And thank you all for your attention. and these are the reference that we use. Thank you so much for your attention.